Famine and Warming Part 2. Did I say it was getting warmer? Turns out that lake effect snow, like you see here, is directly coupled with global warming. We didn't go looking for this. We looked at some meteorological records over the last 100 years to better understand the climatology of the central New York region. And what we noticed pretty quickly was there was an increase in snowfall, a pretty significant increase in snowfall over the last 100 years. And you can see here, going from around 160 or so centimeters a year to around 320, 330, occasionally up to 500 centimeters of snow per year. This is a change that occurred over the last 100 years. And depicted here is only 85 years. But I need some room here. Come on. Space, buddy. This lake effect snowfall is distinct from non-lake effect snowfall. Now, we determine this by the backtracking of moisture packages that come into the region. So it's clear there's a difference in the type of snow that's falling. Does this show up in any kind of permanent record? Ultimately, we're looking at ways to reconstruct climate over the long term and better project climate into the future using those glimpses into the past. So what we did was court a couple of lakes in the region. Cayuga, Owasco, and Atisco Lake are all finger lakes of the 11 finger lakes in New York, and they produce calcite crystals from a macroalgae called a charophyte. So what we did, we cored these lakes and we analyzed the calcite sediment for its oxygen isotope value. And what you can see here, going from 1915 to the year 2000, is a decrease in the oxygen 18O value of the calcite. That means there's probably very likely a decrease in the isotope value of the water that's entering this lake. It just so happens that the oxygen isotope value of lake effect snow averages around -17, -18. Non-lake effect snow has a value of around -8, -9. So a very significant isotope difference that's going to show up in the lake record. And that means it's a permanent record. If we core these lakes back to the beginning of the Holocene, as we've done for Cayuga in particular, we can maybe infer increases and decreases in lake effect snowfall over a given period of time in the last 10 to 12, or in the case of Cayuga Lake, 13,000 years. Now, other climate changes in the 20th century include some regional anomalies and some global changes. In the Arctic, extensive land areas show a 20th century warming trend, in some places up to 5 degrees centigrade. Over sea ice, there's been a slight warming in the 1961 to 1990 period. We don't have much data, though, so take it or leave it. It is what it is. Arctic sea ice extent has decreased by 2.9% per decade over the 1978 to 1996 period. The sea ice has gotten thinner, and there are now more melt days per summer. The extent of ice in the Nordic seas has decreased by about 30% over the last 130 years that we've been keeping track of it. Regions underlain by permafrost have also been reduced in extent. This is making more and more news lately for some of its knock-on effects. In particular, in Russia, the oil fields located about here in Siberia are currently threatened by melting permafrost because the infrastructure for the oil industry is built on top of frozen ground. If that ground melts, that structure on top of that ground, that now muddy ground, is going to collapse. We've also seen a significant decrease in spring snow extent over Eurasia since 1915. So throughout this region, we see decreased snow in the springtime. We also observe something similar in North America, but I don't have stats on that right now. Projected reductions in sea ice extent are important because they're going to decrease the under-ice biota. They're going to change the spring bloom in the marginal zone, and this ultimately affects all levels of the food chain. From the diatoms you see growing underneath the sea ice here, to the krill that pick those diatoms off, ultimately to the whales that eat the krill. And as you'll see, the penguins eat the krill as well. The result is marine mammals and birds all have life histories that tie them to specific breeding sites and times. These will be severely affected by shifts in their foraging habits and migration of prey species. So when the prey goes, the predators go. Now, we've been monitoring the biological activity under sea ice. You can use contraptions like this that capture falling diatoms, for instance, and measure the changes in seawater chemistry associated with this biological activity. So we took a look at what's been happening to penguins over the last 40,000 years. Initially, we thought we might get a 10,000-year record. We were pretty surprised to go back this far, well into the Pleistocene. And this is a story of the anthropogenic effects, surprising knock-on effects of the activity of people that are going to turn out to influence the behavior of these guys and girls. Okay. Kuhn has left the room. Should be a little quieter in a second. Okay, so these are Adelie penguins, one of the 3 species of brushy-tailed or Progoscillus penguins that are found throughout the Antarctic region. So what we observed by looking at isotope values of eggshell remains recovered from rookeries that are extant or abandoned. And we looked at 3 species in total. These are Adelie, chinstrap, note the chinstrap, and gentoo. I don't think this is called a gentoo. 3 closely related species of penguins. We want to look at the history of these species as individual species and in terms of numbers of the individual species. So what can we get from abandoned colonies, from rookeries that are no longer used by penguins? Well, we can examine the occupation history for sure. We can get an idea of sea ice conditions in the past because the krill that the penguins eat are feeding on diatoms that live under the sea ice. Dude, take it easy. We can evaluate population movements, and we can look at dietary shifts. Now, this is what an abandoned rookery looks like. In fact, it's what all rookeries look like, whether they're abandoned or not. We have a mixture of stones that are just the right size. The males pick up these stones, stack them into a nest, and try to attract a mate. And in doing so, stones and penguin guano accumulate over time. So meter squares are excavated, and each layer is then sieved and sorted, and we extract the remains of the rookery from this material, this bird-generated soil that lies above the gravel terrace. So this is natural sediment here, bird-generated sediment up here. We looked at a couple different locations in Antarctica for this particular study. We're going to take a look at, in particular, the shells that were recovered from here and from here, the Antarctic Peninsula. So what do we know about penguin diet? The Adelies eat a mixture of food. They eat krill, they eat squid, they eat a variety of fish. The studies, unfortunately, are from the summer only, when researchers can get there. It's far too expensive to chase these birds around in the wintertime. So we can get down there for a few weeks in the summer, do our thing, and get out before the ice closes us in for the winter. Okay, we can also, fortunately, because of the climate of Antarctica, look at frozen remains from abandoned colonies to evaluate the kind of experiences they had in the past. So this led us to the krill surplus hypothesis, something I hadn't heard of until we did this study. This is related to the extensive slaughter of whales and seals in the 19th and 20th centuries in the Southern Ocean that reduced whale populations by 90 to 95%. Some species are still recovering. This caused the near extinction of Antarctic and subantarctic fur seals, which were real fashion items in Europe at the time. And the net result is, by killing the whales and seals that ate the krill, we have an explosion in krill biomass. We have an excess of 150 tons per year. Now, the whaling and sealing history itself starts in the 1700s. In 1766 on the Falkland Islands and 1786 on South Georgia Island. 1775, 13,000 fur seal skins were taken from the Falklands by a single ship. From 1793 to 1807, it's estimated that 3.2 million fur seal skins were collected. By 1819, They had depleted the seals to the point that they had to move into the Antarctic Peninsula. That's about 800 miles away. And 300,000 skins were taken from the Antarctic Peninsula in 4 years, effectively driving the prey to near extinction. And then they turned to killing the whales. So the whaling began in the late 1800s, began to get very serious in the late 1800s. Have a couple locations here. This is Gardviken on South Georgia Island. This is a whaling station that was established in 1904. And all around places like this, you can see the remains of whales on the beaches. This is on the Antarctic Peninsula, and you can see that certainly the same thing here around Gardviken. From 1910 to 1911, over 6,000 humpback whales were killed near South Georgia Island. This is the Cape Evans hut. Now, one of the things we needed to establish was what's happened over the last couple hundred years. Prior to that, from 40,000 years ago to 265 years ago, we have radiocarbon dates on eggshells, so we know the age of those materials. We have a gap between 265 years ago and today that we have to address somehow. And the reason we needed to address it is we got the data, and I said, this is crazy. We went from pretty steady state values for 40,000 years to a huge change in our 2003 data set. Something must have been wrong, maybe. One way to test that is to look at eggshells that were collected 100 years ago. These are from the Shackleton hut, Cape Evans Shackleton hut. If you want to read a crazy story about some crazy people that did amazing things, read up on the Shackleton expeditions to Antarctica. They had their ship trapped in the ice. The ship was crushed, and they managed to stay alive on the ice for 2 years before sailing in open boats 800 miles across the Southern Ocean to Elephant Island and then ultimately South Georgia Island, where everyone survived. So everyone lived through this experience. Pretty amazing. It's in one book by Shackleton himself called South, and there's probably 20 or 30 other books about that. So those were the people that collected these eggshells that we sampled on New Year's Eve a few years ago, actually about 15 years ago. And this is Steve Emsley, my co-author, and one of his graduate students, Ed, here, collecting fragments of these eggshells that had been sitting in this hut for 100 years. What did we find? The first thing we found was oxygen isotope evidence didn't make any sense whatsoever. It's a huge spread. It's literally all over the place. I looked at the data and I said, I don't know what to do with this. And one of the strange things that happens, seemingly to me a lot, somebody knocks on my door. It's a French bird expert who studies penguins. He wants to have a talk with my French postdoc, Elise, who is working on fish. And I said, so you're a penguin guy. What do penguins drink? He says, they drink everything. Everything. Seawater, freshwater, snow, ice, everything. I said, okay, well, that explains this. It doesn't help us in any way with the penguin biology, but it explains that. The carbon evidence, though, is different. So as I mentioned a minute ago, pretty much steady state for 40,000 years. And then, bang, we have a huge decrease in the carbon isotope value in the modern. We went to that hut, collected some eggshells that were 100 years old, and they look like the modern as well. So whatever happened to the penguin's diet happened somewhere between 265 years ago and 100 years ago. We looked at the nitrogen isotope values going back 8,000 years, and what we can see are some changes in nitrogen isotope values that mirror the changes in the carbon isotope values. But nitrogen's a little bit different. It's a better indicator of diet, perhaps, than carbon, in some ways at least. So we have a couple prey items here. This is ice fish, this blue. This is dragonfish and emerald rock cod. These are 3 fishes that the penguins consume. And then we have krill sitting way down here. So krill, being lower on the trophic level, lower in the food web, has a lower nitrogen value, around 5.5 or so, compared to 12.5 or 15 for some of these other prey items. So we see the penguin nitrogen values transitioning towards krill. So that holds together. So the fossil samples are all here, indicating they're eating principally fish. The historic samples indicate a transition is occurring. And then the modern samples, the moral of this story is we went south to kill the whales for makeup and watch oil and lantern oil. Whale oil burns very clean. It's not sooty like kerosene. So people preferred that in their lamps. That's what we're killing the whales for, fat, and also baleen. The filtering structure in their mouth was used to make women's clothing, corsets in particular. So we kill the whales and the seals for fashion, and the krill population explodes. The Adele switch to eating krill. Then we bring the whales and the seals back, and we institute a huge krill fishery. Again, for cosmetics. In this case, it's the krill rather than the whales. And the result is the Adeles get used to eating krill, and then we take it away. And their population crashed 50 to 70% in some locations in the Antarctic Peninsula. Gentoos seem to be doing just fine. I call them the teenagers of the penguin world. They'll eat anything. They don't care. And subsequently, they take advantage of the real estate that's opened up by the disappearance of the Adele. Chin straps have a different kind of biology, so they're affected by the krill changes, but not as much as the Adele, not as little as the Gentoo.